Welcome back. Our next speaker is András Némethi from the Renyi Institute, Budapest. And he will talk about lattice cohomologies.
Yes, that's the title. That's it. So I will start with the definition. It can happen that maybe everybody knows about the lattice cohomology, what's the definition, but still maybe better to remind you. And after that, I would like to present a couple of cases that what is the lattice cohomology of curve singularities, surface singularities, the topological version, the analytic version, and higher dimensional. So this is for any isolated singularity, one can define the lattice cohomology. So the definition starts that we start with a CW complex, and we fix also the cell decomposition. Yes, so the cell decomposition is fixed. And then we start with a weight function for each cell. We have so the cells Z. And these must have two properties. The first property is that if I have a face, so that is a face of a cube, then this should be so smaller than the face, the weight of the cube, and also is bounded below. So these are the properties. So this is a very general case, and then you have many times such a weight function. And then how the construction continues. So for any integer, we construct a space Sn in such a way that this Sn is the union of all the cubes, such that the weight of the cube is less than n. And then we consider for any q positive HQ the lattice cohomology of this complex, and W is the sum of n. Of course, this will be, because if it's bounded, that is bounded, basically I will have a minimal W, say, which is non-empty, and after that we will have the spaces to the tower of spaces, and corresponding to that we will have the usual S and Z, so that is the usual cohomology. Of course, that you can define also the homological version. And yeah, so what is important here, what I would like to emphasize, that we have the double grading, so I have the Q grading, so that is corresponding to this, that is Q, so we have altogether the H star, yes, we have the Q grading, we have the N grading, what corresponds to this decomposition, and also have a ZU module structure. So that because if we have this inclusion, Sn plus 1, then so each HQ has the ZU module structure. So this, of course, that gives each from S plus 1 a restriction map, and that is exactly here the U action. So in this direct sum, I have a U action, and that U action is exactly this one. Yes, that is the U action. Is the corresponding to the inclusion, I have a restriction.
That's just a
match. That is just a restriction. Yeah. And but that gives so it somehow links the different graded pieces in the ZU module. Of course, this has also, actually, it's very important to introduce also because you see, this is somehow a tower of spaces, and all the time, at least the H0 survives. So I want to see that when Sn is contractible, so I would like to see exactly the reduced homology. So we have the reduced cohomology, which is the sum of reduced homology of Sn species. And then we have a ZU module decomposition. I have a tower of Z's plus the H, so H you will decompose as a z plus z plus z somehow infinite tower, yes, and plus h cube reduced. And somehow the vanishing of these, for example, means that all these spaces are somehow contractible. And sometimes in all the applications what I will present today, that it can happen that we assume, but basically this is in most of the cases can be proved, that this is basically even this, it's a finite Z module. So it's the ranks, basically that's what I want, that the ranks are finite, the Z ranks are finite. And then we introduce the Euler characteristic of the lattice cohomology. And I will write here somehow the definition. I cannot explain because maybe that takes time, but it's the minimum of W plus, and no, of course, that I cannot make the summation over all the ranks, the Betti numbers, because I have infinite tower and they are not vanishing, so somehow I have to separate the reduced part and the tower. That comes from the tower, where the tower starts, and after that, minus 1 to the cube, the rank of each Q reduced. So this is the Euler characteristic. Somehow this place. So basically, what I want to convince you that this is somehow that is a cohomology theory whose Euler characteristic is a number, and I will provide a couple of examples. So that is a categorification of the Euler characteristic. That's what we usually say, that it's a categorization of a number, is a cohomology theory whose Euler characteristic is that number. So now I want to give examples, that categorification of the delta invariant of the curves, of the geometric genus of the surface singularities, or the Seiberg-Witten invariant of the Linkops manifolds. They are all categorification. Of course, that we know that the Hegar-Fleur is one, but here for the links of surface singularities, we give a lattice cohomological interpretation or new definition, new categorification. So how it appears usually, so in many cases, what that CW complex is that CW complex is basically associated, or maybe in this direction, I take a lattice or part, or maybe the first quadrant of a lattice, and then we fix a basis. Yes, and that gives somehow a cell decomposition, gives a cell decomposition that is a lattice point, that is R plus E I, and we have very nice lattice decomposition, or not lattice, cell decomposition of R to the R. So of course this space is very trivial, it's not very complicated, but the weight function provides something new. So the weight function is strong. So if I have something like this, and I introduce, somehow I define a weight function from the lattice points to Z, which say it's bounded below. So for example, a quadratic, positive definite quadratic function or something like that. Yes. Then for any cell, we define that is the max of the weight of the vertices. Yes. Then you see this is a rather arithmetical. Even if I introduce a quadratic function, that the max of this can be very tricky. So somehow what I want to measure here, that the SN spaces are somehow the ellipsoids, but not really the real ellipsoids, but I have to measure that how the lattice points enter on the real ellipsoids, and that's what those are the spaces SN. So from this starting data, then we will have, and using this definition, we will have a lattice cohomology. So let's see some examples. Oh, sorry, I'm very slow. So if I have a curve singularity, isolated curve singularity, so not necessarily plane curve, then we can say I have R irreducible components irreducible components, then we have the normalization map, and then basically this gives, so that is, so the coordinates here that the coordinates, or even each of them CTR, and then this gives a variation. So this is the lattice, that gives the lattice, yes. And then the lattice, in the lattice I have the variation, so this gives variation, R variations, and gives some kind of Hilbert function, given by the Hilbert function associated with the variations. And then we define the V0, so the weight as of a lattice point. Basically, here I can take maybe this one is much better. The 2 times the Hilbert function minus some of the Li's. Again, I will not explain why I'm taking this. Somehow it comes also from a duality. I can rewrite in different way, but then I need also the differential formula. This is no fine for us. Well, using this and then taking this definition for any cubes, we have a lattice cohomology. Of course, it would be wonderful now to give you some examples, but we don't have time. H0, so basically if R, I have R components, then H0, H1, HR minus 1 can be non-zero, starting from R is 0. But really H0, H1, R minus 1 can be non-zero. And that measures rather interesting invariant. What maybe I can emphasize that the other characteristic of this is the delta invariant. So that is a somehow categorification of the delta invariant. So why is this, maybe just a few words that why is this useful? So I have the delta invariant, I told you. So with some, so maybe this is the first property. The second property, with some extra words, we can, if C is a plane curve singularity, then I can recover the Hegar-Fleur link or not, theory of Oswald, Szabó, Rasmussen. So it's almost, so it's actually even, so it's equivalent more, so we can recover this theory. And then why actually I wanted here really to work with this, and then because I wanted to understand the formation of curves, which is, everybody knows it's an open problem. We don't know really that the agency's properties of even for plane curves, that what can be deformed with what. So here we have even the functoriality that if CT forms, that is a flat deformation, then actually for 0 I will write that is for t equals 0, we have a map for t not equals 0, that is a Grady ZU module morphism. So that somehow gives really a powerful tool to, and I really hope that this will be continued and we will have more consequences. So let's see the second example. Second example is the X is a normal surface singularity. Maybe I write surface singularity. And then again we go to the resolution, and that here we have the EIs, the irreducible exceptional divisors, and then that gives a lattice. Again, using this fixed, so we have Z to the number of EIs, and we have a lattice with fixed basis, so we have a CW, so we have decomposition of cell decomposition, and then we would like to have no weight function. So we have 2 versions. The first version is the topological version. Topological version is that I introduce for L, so that is a divisor, yes, supported on the exceptional curve. Then we consider the Riemann-Roch function. L plus, yes, that is a canonical class, yes, but that is topological. I need only the C1 of that, yes, C1, and that is by junction formulas, it's topological. So, yeah, and so this depends on a resolution graph, basically. Well, again, we introduce this one, the VQs, and that gives a lattice for the immediate. I will explain why I'm writing this one here, topological lattice cohomology. The point is that this depends only on the link. So not on the resolution. So that is the main point. So that is actually will be a topological invariant of the link of the three-dimensional manifold. And maybe I also emphasize that one, that here the algebraic characteristic of this is the Seiberg-Witten invariant of the link associated with the canonical species structure. Actually, here I can do even more, that if I introduce another weight function, and here, yes, everybody knows that if that is corresponding sum of the trivial bundle, but here I can twist, I can take other C1s, yes, here the K is a characteristic element in the lattice, then if I vary this, then I will have different species structure of the link. So in this way we will have, actually it's graded, this will be graded by maybe the link, and graded by the species structures, maybe I write in this way, species structure of the link, an extra grading, and then we get that the algebraic characteristic will be the Seiberg-Witten invariant of the link when we consider all the species structures. Maybe if we continue here, just that this is, you see a categorification of the Seiberg-Witten invariant. In the topology, we know many more, yes. So, categorification actually is a fact, and that is non-trivial fact, that this theory, the H, yes, of the topological, coincides with the Hegar-Fleur, that version of the Oswald and so on, of the three manifold. Of course, this is defined only for links of singularities, and let's assume that the link is a rational homology sphere. Yeah. Well, the second version is the analytic lattice cohomology of the surface singularities. Again, I have the very same lattice, but now we want a different, say, analytic weight function, which is not the Riemann-Roch function. So we'll be, again, we will have a filtration, yes, the divisorial filtration of the local ring, and that gives, yes, filtration. We have Poincare series, and we have the Hilbert function. So we have the Hilbert function associated with the divisorial filtration, and we consider here H of L minus H1 of the O of L. Yes, L is a divisor in the resolution, and then we consider this difference. And again, I don't have time to explain that why I'm taking this weight function, but this again gives a lattice cohomology of, say, analytic lattice cohomology. Again, it's independent of the resolution. So it's really the analytic germ. I measured analytic germ. The algebraic characteristic of the analytic lattice cohomology is the PG, which is the H1 of OX tilde, which is one of the most important analytic invariants of the singular germ. Yes, that is, so again, I don't have time to explain why it's so important. And well, this is no analytic, so it's not topology. So it's, you really measure the analytic type. And then maybe I say also that in this case, actually it's, I have a map, so that is the first, that second point. And the third, that we can even measure that if I consider a normal surface singularity, from this cohomology we have to this topological lattice cohomology a ZU module, graded ZU module morphism. And here just, I have 1 minute, and I would like to, maybe 1 minute is not enough, but if you allow me, just to, that this analytic lattice cohomology really measures the analytic type, and that's very, very hard problem. I don't know if anybody knows that if I fix a topological type, that what are the possible analytic structures? That would be extremely important to characterize, at least give some stratification, at least the stratification that give the name, that this is Gorenstein, non-Gorenstein, Kulikov, something, those analytic types. Well, I tell you in this case, that is a topological type. That is a normal surface singularity. This is a resolution graph, negative, definite, that can be realized. Well, one can ask that how many or all the possible analytic structures, if n is only one tau singularity, is the Laufer classified. But in this case, we have many. It's not so many different ones. So I have the Gorenstein singularity. Okay, and in this case, okay, that is the picture what I will use. This is H0. That means that here I have a Z, a Z, a Z. That is a Z, a Z. And here is the infinite tower. Here it's contractible as said. That is the 0 level. That is the -1 level. And this means that here is the U action. Yes, that is the inclusion of Sn. So yes, so that is, I have here Sn, 3 Sn components, 2 Sn, S-1, 2 components, S0 is 3 components, and here it's 1 component. And these are the inclusions. So the inclusions, of course, in this way, because that is cohomological action. Well, that is the topology, and then the point is that all these cycles have some meaning. That is the minimal cycle of Artin, that is the canonical class, yes, of the goal of that Kx what appears. So all of them have some meaning. So where I have the Gorenstein analytic type, then the graded root, so that is the A0 has this type. It's Gorenstein, yes, Gorenstein, but the Z mean it's the Z max. So the divisor of the maximal ideal is not the Artin cycle, but it's double of the Artin cycle somehow. I have another analytic type, the Kulikov analytic type of this singularity. That is actually not any singularity can have Kulikov structure, but this has. In that case, the A0 of the so these are the A0 of the analytic lattice cohomology looks this one. So in this case, for example, this means that the Artin cycle is the cycle, the divisor of the maximal ideal, but it's not Gorenstein. And I have the generic type, or that is something like this, that, yeah. And that's why I'm doing in this way. That also that is also not Gorenstein, and also the Z-min, it's not the Z-max, and so on. And here it's here the PG is 3, here the PG is 3, here the PG is 2. So we have different analytic. We really see that is what I wrote here. The Euler characteristic is the geometric genus, and then in that case can be 2 or 3, and also that we see also in the graph. But so maybe I should. So maybe I should tell you just a conjecture, because maybe 30 more seconds. I conjecture that this is injective. This map is injective, and also somehow that all the possible, so that is fixed topological type, and all the possible ZU with some properties, ZU modules of the topological type measure exactly some stratification of the possible analytic types. So somehow from this combinatorial, I fix this one, and then how many ZU modules I can have with some properties, that will give some information about that. What is the moduli space of the analytic types? Is that topological type fixed? Thank you.